Here we are talking about summing power, and really what I want to go through here is talk about the trade-offs and some of the special requirements that are different from power dividing when we talk about power combining. My name is Shaun Moore. I'm the CTO of Quantic TRM. Today we're going to be talking about some power combining, and it's a very interesting topic, and I hope you enjoy the content.
My name is Eric Zumiez. I'm the Director of Engineering here at Quantic TRM. I'm going to join Sean after the presentation to have a little Q&A and more discussion.
So for the agenda today, what we're going to talk about here really is what is power combining at a very high level. Then we're going to go into the differences between two major subgroups of power combining. One is coherent power dividing, and the other one is non-coherent power dividing. In both cases, we have to talk about where does the non-combined energy go, or where does the combined energy go for that matter. We're then going to go through different types of combining as far as the different methods that we can use to effectively combine power. Going to have a summary, and then we're going to talk a little bit about Quantic TRM, and then we're going to have a little discussion there talking about some other aspects of power combining that we may have missed. So what is power combining? Power combining is the instantaneous vector summation of multiple input signals. And the word vector is key here because we're not looking at averaging of taking average power and just literally summing it up. What we are doing is we are taking an RF signal, which you think about it as a vector, and then we are adding another vector to it. Depending on the phase relationship between those two vectors, energy can either be summed, in which case we have constructive interference between those two signals, and in that case, the summed energy is transmitted through out to our load or whatever we're looking at. Or if some of that energy does not align from a phase standpoint and the vectors are not pointing in the same direction, the energy gets subtracted and that energy actually gets put off as wasted energy somewhere else in the system. What we're going to talk about here in a little bit is exactly where does that go and why do we care about that wasted energy. Before we get into that detail, we have to talk about the two major applications of where we're going to be combining energy. One is coherent combining, and the other is non-coherent combining. So with a coherent combining, what we are looking to do is increase the total power available from a source. A good example of that is say, for example, you need to have 20 watts available to your output, but your amplifiers can only generate 10 watts. In that case, what you want to do is you want to take your source signal, you want to divide that source signal so that you have two equal signals, run them two amplifiers that are exactly the same, and then take those two signals and then combine them together. In that case, you can have two 10-watt sources creating a 20-watt total signal. In a non-coherent combining situation, are cases where you have multiple sources. They could be different frequencies, same frequencies, all sorts of different variations from there. And then you want to put them onto a single transmission line. Say you have, for example, a single antenna, in which case you want to use multiple radios. You're only using one antenna. And in that case, when you use the combiner, you will have two separate 10-watt sources. But when you combine them, you will actually lose half the power, or 3 dB, of each individual signal, but they will get put on the same line at half that power. Therefore, what you'll end up with is two signals at 5 watts in the example it's on the screen on the right. And this is sort of a very high level discussion as far as to what the difference between a coherent combiner, where you're trying to take a single signal and then increase its power by combining the power of multiple amplifiers, or in a non-coherent signal where you're trying to take two separate sources and put them back together on the same line. At very low power applications, this happens all the time for the non-coherent case, in which case that wasted energy is so low where it really doesn't affect very much of the circuit. However, if you're talking about some very high power transmitters, that wasted energy can create a tremendous amount of heat, and it needs to be considered. So again, is a little bit more elaboration of what I was just talking about with coherent power combining. We're taking two signals that are the same, both in frequency, amplitude, and phase, and we're summing them together. This conserves all the input power and delivers all that power to the output. No power is lost. If we have non-coherent combining, where the signals are not exactly the same, the power delivered to the output is the vector sum of what all the inputs are. The difference or the vector subtraction that happens does not get delivered to the output, and it gets dissipated someplace else. In isolated power combiner, which we're going to talk about in a minute, is the difference between an isolated power combiner and a non-isolated power combiner. But in an isolated power combiner, all that energy is dissipated internal to the combiner as heat. In a non-isolated combiner, that subtracted energy gets reflected back to the original sources, and that shows up as a higher VSWR to those sources. So how do we actually think about, why are we losing power when we're combining? Because it's sort of not really normal to think about losing power. If I'm putting two things together, I should sum it, and I really shouldn't be losing power. But what's a simple way of thinking about that? Well, if you have two separate signals, and you have a resistor between those two signals, and you think about the voltage built up across that resistor, if it's coherent and those two signals are equal in amplitude and phase, you're not going to see any voltage build up across that resistor, no matter how much power gets put into it as that sine wave of that signal goes through the system. And in which case, for that case of a coherent signal where they're the same, where no voltage gets built up across that resistor, all that energy will be delivered and combined to your final load. In a non-coherent case where either the frequency, the phase, or the amplitude is different, you will generate some voltage across that resistor. Well, that voltage that you've generated across that resistor will necessarily not add, and it needs to get dissipated someplace, in which case, and this my very crude example here, the resistor will be dissipating some power if the voltage is different. So the big thing here is to think about coherent and non-coherent signals, and a simple way to think about this is if you think about taking those two signals and just dropping them across a resistor, will that resistor see voltage across it? If the answer is yes, then it's non-coherent. If the answer is no, then there won't be any voltage across it, that we're now looking at a coherent system. As with all RF circuits, power combiners work to have a good VSWR on all ports to minimize power loss. So this example of putting a resistor across two signals is just really an analogy to help understand the difference between a coherent and a non-coherent signal. So how do we estimate power losses from near coherent signals? A good approximation, as you can see on the graph on the left here, is that we lose significant amount of power when the phase differential gets significant. That graph has phase error on the x-axis and the percent power loss on the y-axis. And as you can see, that if the phase error between the two signals that we're trying to combine is down, less than 20 degrees or so, there's very little percentage power loss. However, as that phase error gets greater and greater, and as you can see at 90 degrees, we're losing half the power, and at 180 degrees, we are losing all the power. So a way to think about that is if you have two signals and the phases are exactly opposite, they will subtract completely and no energy will actually pass out to your load. That curve that's generated there on blue is a very good approximation of exactly how much power you're going to be losing. It is a half angle sine squared function. So that gives you a very good estimation as for how much power that you're actually going to lose. The graph on the right-hand side of the screen shows the same data in a little different format. The black line that starts up at the top and kind of curves down, that correlates to the insertion power loss due to on the insertion loss. That goes over to the graph on the scale on the right-hand side of the graph as far as dB power losses. The other multicolor lines show percent loss. What's interesting about this is that on those multicolor lines, we are looking at differences between amplitude as well as phase error. And as you can see by the scales there, that really if the amplitude is difference between those sources is less than about 2 dB, there is virtually no difference. Those lines are almost laying on top of each other, and then therefore most of that power combiner loss comes from the phase differential. So the results of this sort of quick analysis here shows us really that phase variation is really the driving factor for generating insertion losses in power combiners. And a good way to estimate that is if you take the phase error between them and it's the half angle sine squared function. So looking now at the two different types of power combiners, which I did allude to a little bit earlier, are the isolated and the non-isolated power combiner. The isolated power combiner takes the energy that is being put in there, and any of the differential energy that gets generated is dissipated in heat inside the combiner, whereas in the non-isolated power combiner, that energy is reflected back to the sources. That higher VSWR shown by the sources is a ratio to exactly how much energy is being reflected. I'll show you how that calculation works in a few slides. Right now, looking back at the isolated power combining, there are several ways that we can go ahead and design sort of combining network. A big consideration of designing these sorts of devices really has to do with how are we going to get the heat out of the combining network for any differential energy that happens to go in there. Some very good methodologies that we use for that example are like, for example, 0-180 hybrids. Those take either an in-phase signal or a 180 degree phase signal. In the case of the ones on the screen, really, we would use the 0-degree inputs. And any differential energy would be reflected out of the isolated or the delta port of a 0-180 hybrid. Once we get any sort of device where we're having a termination as where the energy is going, that becomes a very effective heat management solution for getting that excess power away from the device itself. So a 0-180 hybrid has an external termination. A ring hybrid, for example, any variety of those will have an external termination. A glycol combiner will have also a high power external termination. If we're going to use something like a Wilkinson power divider, those terminations are internal, and because of the structure of the way that those power dividers are designed, there's usually a very poor thermal path with those to ground, and therefore I will caution using a Wilkinson as a high power combiner because it really won't work that well at dissipating that combining heat. Wilkinson dividers, on the other hand, when they're in the common mode functionality, working as a divider, there's very little voltage being developed across those resistors, in which case they can be very effective and run at very high powers with very low voltage and power dissipated internally. However, as a combiner, that voltage can build up very quickly, and very quickly you will run into an area where you won't have enough thermal path to actually dissipate that heat. Other devices that work really well for isolated combiners are 90-degree hybrid combiner phase networks. They are complementary, self-correcting, and they use an external termination on the isolated port. So very often, instead of having a device like the shown on the screen right now, where we have a power divider and power combiner, if you have two 90-degree hybrids and you flip them, you can end up with a very effective sort of situation. That's what is shown on this screen right here. I absolutely adore using 90-degree hybrids for power combining situations. The networks typically have very low insertion loss, as well as having the ability to offload all that extra heat off to the termination. They're extremely efficient because of the short line lengths that are involved, and because of the amplitude self-correcting that happens here, they're actually more efficient than many of the other networks that we do have available to be able to do that. For a non-isolated coherent combining, this can be a very good option for anybody who's looking at trying to reduce overall insertion loss within the combiner and also help with some of the other sort of thermal management things that we have to deal with. Isolated power combiners tend to have some loss in the balancing network, and that is just due to the nature of adding the extra circuitry that needs to be involved to create the isolated ports. Non-isolated combiners, for example, we can have some radial combiners that can actually go in there and have some very, very low loss characteristics. This sort of a non-isolated coherent combiner can be extremely effective if the phase errors in the amplifiers are very low, in which case then you can have a very efficient power combiner using a very low loss network. Some examples of some radial power combiners are shown on the screen right now. You can see we got some very high port counts to actually have that power combining. Um, and in this case over here, this can actually be a very low loss, very effective solution to be able to generate some very high power combining as far as how this is actually built up. Um, the one thing you have to be careful of is what does the VSWR of that reflected energy uh, do to your overall efficiency, and what does the that reflected energy that is as opposed to having go into an isolation resistor, what does that do to your source impedances? A good way to look at this here is if you look at just looking at some basic principles here, looking at what is VSWR and where does that energy go. So what happens in a not in a near coherent sources for non-isolated combining is that any of that differential energy, and this is that 1/2 angle sine squared energy. If you look at that actual power, and if that gets reflected back to your source, how much additional VSWR does that cause? Well, if you look at the reflection coefficient of the signal based on that sort of power being reflected back, you can estimate what the change in VSWR is going to be. The example that I have on the screen here shows that what we have here is if we start with a 1.2 to 1 VSWR, the reflection coefficient for that is 0.091. If we were to add a 20-degree phase error for that, uh, on the nomograph there, you see that what that does is that adds an additional 0.167 of reflection coefficient based on the reflected power we have coming back for that 20-degree phase error. If you sum the 0.09 and the 0.167, you see that you end up with a reflection coefficient cascaded of being a 0.258, which is a VSWR of 1.7. So in this example here, if you have a 1.2 to 1 VSWR of your combiner, and then you have two sources coming in with a 20-degree phase error, your effective VSWR that your amplifiers are actually going to see will be a 1.7 to 1. Now, this is actually good news because for most systems, you can maintain that phase error less than 20 degrees, and you can still end up with a VSWR under 2 to 1, which is usually about the threshold of what you want to have for damage for amplifiers. So this allows you to use a non-isolated combining system at fairly high power levels, get the benefits of the lower insertion loss of a radial combiner, and still have good overall good system performance. So this is kind of a nomograph that you can go ahead and kind of look at to really to estimate as far as to what is that impact for VSWR going to be based on the phase error of what you're seeing. So if you have a choice to build a isolated or a non-isolated power combiner, which should you choose? Well, if you're putting multiple signals on a common path from multiple radios onto a common antenna, different spread spectrum sorts of sources, then an isolated combiner would be the best solution. Uh, each signal will see a total of 3 dB worth of power loss in that combiner for that total non-coherent situation of what you have going through there. The energy loss really would be too high for the other sources going on through there to be able to have that be as a non-isolated sort of case. The VSWRs would just be very high, in which case you need to have an isolated combiner solution. For this particular sort of solution, 9-degree hybrids work exceptionally well because we can take all the differential energy and put it off to a good 50 ohm termination where we can have some good high power handling capability. If we're trying to increase power where we're running multiple amplifiers in parallel, uh, we can then go with either an isolated or a non-isolated scenario. And what comes down to there is how well are those amplifiers matched And can the amplifiers tolerate that little bit of increase in the VSWR that I just spoke about? If the reflected mismatch energy will be too much for the amplifiers to handle, then you have to go to an isolated solution. If the amplifiers can tolerate the expected power, then possibly a non-isolated solution could actually end up being a better overall solution um, for you. Some examples that Quantic TRM makes here as far as within power combiners. For isolated combiners, um, you certainly can use any variety of higher power dividers, 180 hybrids, 90-degree hybrids, and those sorts of devices. Again, if we're looking at building a power combiner that has these sorts of characteristics, we need to be cognizant of the phase and the exact nature of the signals to make sure that we can get the heat out of those devices. For a non-isolated power combiner, radio combiners can be a fantastic choice. They can, because of the nature of how they're built, they tend to be lower overall insertion loss because we use a lot of airlines and sort of raw sort of construction in those devices. Uh, we work with the impedances to make sure that we have good matched VSWRs and good symmetry in them. And if the sources feeding them are also symmetrical, you can come up with some very good um, low loss scenarios. Um, the isolated combiners always tend to be, I think, the fail-safe for most people thinking about these sorts of things, but they may or may not always be the best solution. So it's always important to go through it and at least look at what a non-isolated combiner could do within your system. So as a quick summary, what is power combining? Um, Power combining combines multiple signals onto one transmission line. If you're having coherent signals, those things will add and your total power will be boosted. If it's non-coherent, uh, and then what'll happen is the some of that signal um, will go through and actually be dissipated in other ways. Um, but if we're, for example, if but that does allow you to share multiple resources, for example, multiple radios up onto a single antenna. Internal power distribution for coherent and non-coherent signals. Signals combine vectorially, resulting in unsummed energy that needs to get dissipated. Um, Non-coherent energy, if it's completely different, you lose about half your power, about 3 dB, need to be absorbed in the combining network. And then overall, we have to go in there and do the analysis to see exactly how much power we're losing and understand that that energy will either be reflected back to as higher VSWR or absorbed in the dissipating network um, for an isolated power combining. And don't forget that a non-isolated power combining can be a very good solution if the signals being combined are coherent. So the key takeaways here really are the most important factor when combining power is to really understand the types of signals that you're combining, and that combining is never a one-size-fits-all discussion. We have to go through there and really understand the nature of the signals and try to um, ascertain what the best overall solution is. Uh, so first, you need to look at is determine how much power that you need to be dissipated in the combining network. Secondly, we have to make the decision is can you dissipate that heat locally? And third is can these sources tolerate the increased reflective power if you do go with a non-isolated situation? After considering the total non-combined power and determining where it can go, you certainly can then make a more intelligent decision as to the type of powered combiner that you're going to be using, as well as the type of actual construction that you're going to be using. A little bit about Quantic TRM. We specialize in passive microwave components, really for unique solutions, whether it be power combining, beamforming, or any other standalone sort of passive component. We work primarily from frequency ranges from DC up to about 40 gigahertz. We build all sorts of power combiners, dividers, directional couplers, hybrids, beamforming networks. We specialize in really highly integrated, customized packaging and working to with our customer to actually fully understand what their needs are. We freely integrate between various technologies. We're not beholden to any one of them within our manufacturing process. And we like to work with our customers to understand really what their needs are to make sure that they get the best solution for their needs. Thank you.
All right. Thanks, Sean. That was a great presentation. Some questions that I think we should discuss. So when combining signals in different frequency bands, are there any other methods that are more effective than the isolating combining you described that's less than the 3 dB power loss?
Yeah, absolutely. And I think a good way to get over that 3 dB power loss is to use a different technique altogether, which is actually using something like a diplexer or a triplexer. That is if the frequencies that you're trying to combine are actually in separate bands, and if they're always in separate and distinct bands. And in that case, you can get very low loss combining without having the penalty of the power combining loss that we get with the sort of power combiners that I described. A diplexer does have the sort of negative aspect of it, if you will, that you cannot use it if you're combining signals that are actually in the same frequency band. So in that case, if you have different frequency bands, you can get away from the 3 dB power loss by using a different sort of device, like a diplexer.
Got it. Nice. How about when you're using a non-isolated power combiner? What happens if any amplifier stops working?
Okay, this is the fear of every engineer going through using this sort of device, because what happens is uh, once that amplifier goes offline, its match goes completely out the window, and what happens is you end up with a very high VSWR, and half of that energy that's still left in a two-way combiner example gets reflected back to its source. Uh, with half power, the VSWR of that other source goes to something like a 5.8 to 1. I think, which is really, quite bad. So if you lose one amplifier, essentially you lose the entire rack. Now, fortunately, most amplifiers do have a high VSWR sensor in it, in which case, if the VSWR goes over some threshold, it does shut it off. So we don't actually destroy the amplifier in the process with all that energy being reflected back. But it does usually result in sort of a shutdown of the entire system as opposed to just dropping some power and dumping that extra power into heat, which is what you get in a little more traditional isolated sort of power combining.
Hmm. Interesting. Talking about different styles of combiners, can you use a Wilkinson style power divider as a combiner? Hmm.
Yes, you can. There's a lot of caveats and a little asterisk next to that you have to fill in. Um, it will work for low power devices. The one drawback of a Wilkinson style power divider using it as a power combiner is that the power rating drops dramatically. For a Wilkinson style divider, there is virtually no voltage across those isolation resistors inside the divider, in which case very little power is dissipated in the divider itself. All the power just essentially just passes right through there because very little voltage is built up across those resistors. For the combining operation, when the inverse happens and you're injecting two different signals into the outputs, the voltage across those resistors can be quite significant. And in that case, you will get significant amount of power dissipation internal to the resistor. Wilkinson style power dividers, by the way that they're designed, they need to have this balanced network. And once you do build a part that has this balanced network, unfortunately, the thermal path to ground to get heat out of that is very inefficient just by the nature of design. So Wilkinson power dividers work very well as dividers from a power handling standpoint. They don't work very well as combiners uh, because of the buildup and heat issue. So you can use them. You have to be very careful with how much power you're running backwards through them. And then at that point, also the matching of the signals becomes very critical. The power limits, for example, usually drop on the order of at least a 30 to 1 as far as the power rating goes. So if you have a power divider that's good for 30 watts looking forward, you're looking at less than a watt as a power combiner. So there is a very significant difference.
Good to know. Thank you. How about what's the easiest way to estimate how much signal will be lost when combining near coherent sources?
Yeah, so there's a sort of a rule of thumb that we use in the industry, and it has to do, and this was in the presentation. I'm not sure really how well it was highlighted, but it has to do with the half sine squared function. If you look at the RMS value of your error of what your signals that you're combining are, take half that angle or that phase difference and take the sine squared of that function. That will give you the percentage of power that is lost. So it's a fairly simple equation. Like I said, it's a half sine squared that will give you the an estimate, very close estimate as to exactly how much power that's going to be dissipating as heat or reflected energy within the power combiner.
Got it. Yeah, one more for you. How great is the impact to amplitude variation of a source on the total power delivered?
It does make a difference because if you take a look at what you have, if you have two signals coming in and the voltage and the amplitudes are different, you will create a little bit of a differential voltage across there. However, the phase difference makes a much larger impact. The amplitude difference of a couple tenths of a dB, half a dB, even 1 dB will make a very minor difference in the total power being dissipated in the combiner. Whereas if you get a 15 or 20 degrees phase difference, you're going to be generating some significant heat. So it does make a difference. However, it is a much lower effect than phase. So as long as they're in the same ballpark, usually it's something that we typically ignore.
Thank you.
You're welcome.